SwayamPrabha. Digital India. Educated India.
The first 5 questions or 6 questions what we have discussed, that is the starting point for our course. Okay, what is the first question? Second question? Excellent. Third question? Yeah. Fourth one? No. How does a chemical process flowchart start? That is, I think, third question. Yeah. Fourth question was chemical reaction. What is chemical reaction engineering? And fifth question?
What is the information necessary for reactor design?
Yeah. Information required for reactor design, and then of course heterogeneous, homogeneous and all that we have discussed. Okay. So, we finally ended up with this diagram. Again I am trying to draw this. So, reactor, what is this? Input, yeah, output, this one kinetics, contacting, yeah, then here we have chemical, physical, here we have batch, we have continuous, and here we have PF, MF. Okay. I think that equation I do not want to write. So, please remember this diagram, you will have all the information that is required for reactor design. Okay. Please do not forget that. If anyone asks you what is the information required for reactor design, draw this figure, okay, and then explain what you have to explain, that is what is the meaning of physical kinetics, chemical kinetics, batch and continuous, and we have also discussed when do you choose batch and when do you choose continuous. Okay. Physical chemical also we have discussed it, saying that in physical kinetics when you say, sometimes you will be surprised, I will derive also after some time, that kinetic expression will not be there at all, chemical kinetic expression will not be there at all. It is only the physical equation, mass transfer equation, that is what you have to substitute in the reactor design expression. That is what is your minus RA. Your minus RA will be simply Kg into CAB minus CAS, where CAS is concentration on the surface and CAB is concentration on the bulk, in the bulk. Okay. So, that is why that physical kinetics will automatically come into picture, that we will do derive later. But when you are talking about continuous and contacting batch and continuous, when do you choose batch system? I think we discussed, I think it is better for me. Huh? Okay, small production rates. Okay. So, then that is the only criteria, or is there any other criteria?
It is slow. When you
very slow reactions, yes. Yeah, it is not residence time you can also use the continuous system. Yeah. So, that is only criteria.
When you have
what did you say the first one? Batch,
small scale production.
Small scale, and then second one what you said is very slow reaction, that is all. There is another one important point.
Flux. When you have unsteady state,
batch reactor is always unsteady state.
Seasonal production.
Yeah, flexibility in production, that point also is very important. When you need some flexibility in production, that means you are not dealing with one product, you are dealing with maybe 5-6 products. So, if you have 2-3 batch reactors, you can produce any time these 2-3 products. Okay. That means there is no continuous demand for the products. So, based on that you will choose which product you have to produce now, for that batch is the best system. So, but automatically that total production rate also must be small, it cannot be very large and then still you have flexibility, right. When you want to have that kind of flexibility for very big size plants, you have to go for only continuous, that is all. I mean, there is no other choice. Okay, good. So, that is why that important point also, please remember 3 important criteria. Many books will not give this information, even if they give, they will simply write in one corner one sentence, where you do not have, you cannot go to that particular sentence and then remember it. So, that is why I am telling you these are the things, basic things that is required before we start reactor design, actual expressions, because you should know what is the information required, you should know what is the meaning of chemical kinetics, physical kinetics, because this will differentiate whether you have heterogeneous reactions or homogeneous reactions. And here when you come in contacting, you would like to have contacting either continuously or batch. And now if you get a job in industry, when you go and then people may ask you, okay, now we have a new product coming this size, so you design the entire plant, means you should know that, because entire plant design starts with only reactor design first. Okay. So because you have a stoichiometric equation already they would have given you, then they will also tell you production capacity, or otherwise they will ask you to go for literature, not literature, what is that, market survey, and from market survey you will get what is the production rate, and if it is very large you automatically decide continuous. If it is small, then I told you maybe it is 10 tons, 15 tons, 20 tons, okay, or 1 ton definitely yes, but we have some some gray area where maybe between 10 to 100 tons whether you go for continuous or maybe batch. So for that you have to now simulate the whole system on the computer and then try to find out economically whether it is feasible to go for a continuous system or batch system. But if you have, let us say 10,000 tons per day, if you want to produce, definitely there is no choice, no batch, you have to go for only continuous. If you are going only for 1 ton, again definitely you have to go for only batch. I think there is no point in designing a continuous system for that. So these are the things. So then again we have also discussed, in continuous we have two choices, plug flow and mixed flow, and we discussed in last class that plug flow you will go for only very short residence times, and the short residence time is mainly for gas phase reactions, because gas phase reactions are very fast. Even if there is catalytic gas phase reaction, the reaction time is again very small, seconds. Why? Because by definition of plug flow you have to maintain very high Reynolds numbers, velocities, right. So when you are maintaining very high velocity, if you need very large residence times, your length of the reactor will be very large. You cannot have automatically diameter increasing, because when you are increasing the diameter you cannot maintain plug flow, right. Plug flow means flat velocity profile, right, one of the definitions, which is also right, but the correct definition is each and every particle must spend exactly same time there. So that condition will come when you have only flat velocity profile. Flat velocity profile fluid mechanically you get only when Reynolds number equal to infinity. So that means velocity equal to infinity if you fix this as diameter. So when velocity equal to infinity, you cannot provide length by infinity, always 0 velocity, length by velocity equal to T bar, mean residence time. So this velocity is infinity, means you can provide only 0 time in the reactor. So that means all plug flow reactions theoretically speaking should have 0 reaction time, because we do not use 0 reaction times. So we now say that if the reaction time is very small in minutes or seconds, then you go for only plug flow. And all packed beds are also imagined as plug flow reactors. Why? Because you can very beautifully get a flat velocity profile in packed bed reactors. That I will discuss when we are coming again to separately designing packed bed, not packed bed, plug flow reactors. Okay, good. So now mixed flow. Mixed flow generally used for very okay, another thing also for plug flow. So okay, one is residence time. What is the other criteria? Exothermic reaction. Because it is impossible to maintain isothermal conditions in a lengthy reactor. Okay, it cannot. That also we will discuss when we talk about plug flow reactors again. It is not possible. There will be definitely some temperature variation, and if you want to have exactly one temperature in a plug flow reactor, you should know you should put infinite number of heat exchangers with different capacities. Okay, that also I will explain to you. So that is not possible. That is why if highly exothermic reactions, you automatically go for mixed flow reactors, wherein due to mixing you can maintain one temperature and one concentration. That is the definition of mixing by the by. Okay, so those conditions. Now if you come to mixed flow, when you have very large residence times like liquid phase Liquid phase reactions will take place in 8 hours, 10 hours, 15 hours. If it is biological wastewater treatment, I told you 3 weeks, 4 weeks, 1 month. 1 month is 4 weeks anyway. Okay, yeah. So much time required for liquid phase reactions, and many industrial reactions will be definitely between 4 to 12 hours. You should have seen in the labs also esterification reactions, esterification, saponification reactions. These reactions are 6 to 8 hours or 6 to 10 hours. Okay. So, to provide 10 hours mean residence time, you need a tank, because the flow rate and volume of tank will give you that much residence time. That is the reason why you go for mixed flow system for liquid phase reactions. And another best advantage for liquid mixed flow is that exothermic reactions. If there are exothermic reactions, happily go for mixed flow, and mixed flow is the best to control, right. So, this is the criteria. So, now let us start deriving first the batch reactor. Let us take batch reactor, and afterwards we will take continuous reactors. Okay. So, we are now discussing about derivation of ideal batch reactor. Yeah. So, you know very well that all the batch reactors, normally in our textbooks we will have drawn something like this. There will be a jacket, and then you will have a stirrer, this is closed. Then you will have a pressure gauge, then we will have temperature. Okay. So, of course, here you may have temperature measurement through thermocouple or something. Thermometers no one will put, but thermocouple. Okay. Good. Yeah. So, this is how it looks, and we will fill up normally till this point. And when you are talking about reaction mixture, that volume, when you are deriving it actually, so that when you are calculating, that volume will be only, this is the volume, reaction mixture. This we call it as vapor space. In case the reaction is taking place around maybe 120, 150, if the vapor pressure of this reactant and mixture, reaction mixture is more, then there will be some vapor forming on the top. So, that has to be there. Okay. So, you cannot also take it out continuously, because concentrations may change. So, that is why you just leave it and then close everything, and there may be dangerous chemicals where you have to really tightly close, okay. Or otherwise if it is very harmless chemicals, even without the top also you can conduct the reaction. Okay. That means this part will not be there. That is not scientific way of doing, and but anyway that is also possible for us. So, this is the one. And why do we call this one as ideal batch reactor? What do you mean by ideal batch reactor? So, in all these reactors we are assuming that we have only ideal conditions, ideal contacting. Okay? And first of all, the question is, why should we assume this ideal condition, and what is this ideal condition? So, the ideal condition for batch reactor, what do you think? What are the conditions? Why it should be? But normally what we do in the batch reactor, we put the concentrations at time t equal to 0, okay. At time t equal to 0, Ca may be Ca naught, some concentration, and after some time greater than or greater than 0, you will have Ca equal to some concentration which is a function of time continuously decreasing if it is a reactant, or if it is a product continuously increasing, that much we know. Then we will charge the reactor with whatever amount, maybe 1 ton or 500 kgs or whatever, and then we start stirring. Normally what we do is we start the heating system if the reaction is taking place at high temperatures, maybe 100 degrees centigrade. So, till then, even though we have the reactions there, all that we do not consider. Even though we can consider, definitely we know how to do that, not much mathematics are required, but still we can do that. Yeah. So, then we will wait till that reaction time is complete. How do you know that that reaction time is complete? That is what we are going to derive now for from the equations. Good. So, this is what, and as someone was telling that okay, I have this setup and I put this and I started this stirrer, and what I expect inside the reactor is at any time inside the concentration of Ca and temperature must be uniform throughout. Okay, that is the ideal condition. Okay, ideal condition is concentration and temperature must be uniform throughout the reactor at any time t. It is only uniform, it is not same. It is not, if it is same means there is no reaction. All the time if it is same only Ca naught, then there is no reaction. Okay, it is must be uniform throughout at any particular instant of time when you look, right. So okay, now my question is, this is the condition for ideal batch reactor, but why should I assume that? What will happen if I do not assume?
To calculate the final conversion or yield, you need to make this assumption, otherwise we cannot calculate how much of the reactants are converted into products.
Why? I think because I can take always sample and then find out what is the concentration.
Mathematically won't be able to. Every molecule have different concentration because it's not uniform everywhere in tank.
So
we cannot say at what time the reaction will be completed.
Any other ideas?
Non-linearities are generated due to assumption of non-uniform concentration through
What are the non-linearities you are talking?
dependency of concentration.
But what is the meaning of non-linearity first of all?
If we consider the K equal to K naught is equal to C by RT, where we are
That is there already that equation is non-linear. Arrhenius equation.
we consider this assumption uniform concentration and temperature, some of the non-linearities may be reduced.
No, how can I avoid? See, even though if I have uniform stirring, how can I avoid non-linearity of rate expression with temperature change? Or if I have a second order equation, second order rate expression, how can I assume that will be first order? You understood linearity, what do you mean by linearity? There are no flow rates, it is a batch system we are talking.
So we need this to design the actual system. For example, if say in theoretically we can say 90% conversion should be at time t.
Yeah.
And in a practical reactor we are only get 85% of conversion. So it means that we have still have scope for to increase it up to 90%, though it's not practically possible.
But why is it not practically possible? What are the things you have ignored practically?
Because
There are non-idealities.
What non-idealities?
There may not be proper mixing at the
Yeah,
controls.
what are the non-idealities? Because we had ideal batch reactor. So what kind of non-idealities we can expect? Only only mixing, right? What I am asking is, if I ignore that, where is my problem coming? Okay, it is different. If I don't have definitely good mixing, so definitely it will be different. So what?
The concentration, the conversion may not
Yeah,
be different.
that is very important. The rate expression which we are getting, I don't know how to write. The rate expression is a function of temperature and concentration. Forget about temperature now, right now. We only talk about concentration. You have non-ideality, that means it is not uniform mixing. So it is a function of concentration. Next question is, which concentration? The concentration here or here or here or here or here, where? Yeah, but definitely my problem is solved if I am able to have throughout only one concentration. Then I know definitely my rate is a function of that concentration. Otherwise, if the concentration is changing at various places, now I should measure at each and every point. I should get some average of that, weighted average. For example, in this volume, I take 1% volume, what is the concentration? I take 5% volume, what is the concentration? Another 1% here, what is the concentration? Another 10% here, what is the concentration? I have to sum up all that and then take some average, some volume average, which is headache for me. Why? because fluid mechanics already taught me that you better design a how to design a stirrer. So, you do very efficient stirrer. So, naturally you will avoid all that measurements here. First of all, how do you measure? You have to put infinite number of probes there, okay, if you are directly reading. Otherwise, like how you took the sample using pipette like that, how many pipettes you have to use, what length, and that fellow is stirring inside, that may break the pipettes. All this, why is that problem? Simple problem is design a good stirrer mixer, your problem is solved. So, that is the beauty in assuming that we have ideal batch reactor, ideal mixing. Okay. Now, I think because most of the time we will not discuss this part, we will say that assume uniform mixing, that is all we say, so that it will give you uniform concentration and uniform temperature, but we never ask so what, if I do not assume, what will happen? What will happen is your life will be miserable in measuring in at every point, and after that you have to average it out. Okay. So, some kind of weighted average, or either weights you have to use, volumes you have to use, all that. And first of all, how do you measure them throughout the reactor? And in the lab it is okay, maximum I may take 1 liter, 2 liters, 5 liters, but in industry it will be 5 meter cubed, one well, big well. So, that well, I think inside that you are stirring and all that, how do you take the samples there in the well? So, to avoid that, we will say that yes, now I can design a perfect stirrer, and that is much easier for me than measuring the concentrations at various points. Now, let me assume that I have a perfect stirrer where it gives me uniform concentration and uniform temperature. So, that is the meaning of this assumption, and if that assumption is not there, then you have a problem to define even what is rate, because rate is a function of concentration and temperature. Temperature is varying at various places, concentration is varying at various places, which rate you are talking. So, when I am writing my material balance, I do not know which rate I have to write, unless you take again some average rate, right. So, that average rate is given by your stirrer, that is all. What you are doing is, instead of you doing all that, you are asking the stirrer to do that, that is all. When it is perfectly mixing, the contents will be only with one concentration and one temperature, so that you can happily measure that concentration, only one concentration you have to measure, one measurement, and then you can write the rate expression. So, once we know that, then how do we write the expressions? Like the material balance, first I think we are doing only first isothermal. Let me also write here, put it in bracket, and non-isothermal we will do it after you learn something from isothermal reactors, that we will do later. So, here, and we have one universal material balance equation, it is a mass balance equation what I am telling. I am not writing energy balance I will write later. So, mass balance equation, always when you are writing mass balance, please remember you have to specify you are writing for which species. Mass balance is always for individual species, whereas energy balance is for whole thing, you do not have to differentiate. Okay? That is the beauty in a heat transfer, because it simplifies, whereas mass transfer every species you have to write, and always in our course that our species is A, reactant A, which is a limited reactant, limited, what is that, limiting reactant, which is a limiting reactant or key reactant, that is also another name what we say, right. So, that means that is the one which is really governing the rate. You heard of definitely what is pseudo homogeneous, pseudo first order for example. Actually, that is the second order reaction, A plus B going to some reaction, then I am taking maybe 100 or 200 moles of B and only 1 mole of A. This is what we call pseudo homogeneous first order reaction with respect to A. Why A? Because I can see only the concentration change with respect to A. With respect to B I cannot see, because I have 500 moles or 200 moles, practically there is no concentration change in that. Okay? So, that is why we have to write only for a particular species, and here we do for key reactant, and all the time when we write mass balance A, that means that is our key reactant or limiting reactant. Okay. The universal equation always what we have is input equal to output plus accumulation plus RXN reaction. okay, where except the problems as I told you, all other things are only written with his hand, including graphs. It is worth seeing. I have a copy, I think I will show it to you once. I have a copy, okay, library copy only, because it is with me, it is not lost. So otherwise I think that also could have gone, I do not know. It is beautiful, his handwriting. Some of his papers also, I will also send some of his papers where he has drawn the diagrams and graphs with his own handwriting, and the matter is of course typed. So that is why all excellent engineers will have very good handwriting. Good. So this is the equation what we have. So now this equation I can simplify if we say that for constant density system, okay, then this will become Na naught by, yeah, V equal to C A naught. Where is the, oh here, yeah, for constant density system, for constant density T equal to yeah, Na naught, because for other sake I think I will just write here, into dxa, oh, integral dxa by minus R A 0 to x a, which is nothing but C A naught minus R A, that is the one, okay, good. And if the other example what I gave, if volume is changing, okay, that means 1 mole giving 4 moles, or maybe 4 moles giving 1 mole, that is volume reduction. Okay. So the volume reduction is given by Levenspiel as, yeah, for isothermal system, we are writing isothermal system, V equal to V naught into where epsilon A equal to 6. So this is the equation, linear equation what he has used, where epsilon A is number of moles initially present minus
initial.
Final minus initial divided by initial, okay, or volume at t equal to 0, volume at any time divided by volume at t equal to 0, okay. That equation also what is the origin and all that I will derive. I do not ask you to blindly accept that, but Levenspiel directly says that assume the variation in volume is linear, okay. So why we should assume or why we cannot assume, we will derive, I will derive and then let you know, okay. So that we will do after completing this contacting pattern. So then for variable volume, you will have an equation T equal to Na naught 0 to x a Na naught, yeah. So then dxa by minus R A into V naught 1 plus epsilon A x a, okay. So this equation I have written now later after that, then this is equation number 8, this will be equation number 9, this is the general expression again for variable volume, and you know this V naught is a constant, yeah, that becomes C A naught, good. So for constant density systems, this if I take here T equal to C A naught 0 to x a dxa minus R A 1 plus epsilon A x a, very good, okay, good. So this is the equation for constant density system, sorry, variable volume system, okay, good. So now this equation he just leaves it without integrating, then of course as special cases you can always do that, okay, and he also puts this in the form of graphs. We are only simply putting this equation in the form of graphs, this integral in fact. How do I plot this integral as a graph to get that area under the curve? Where is this? Yeah, here. Okay, you see this dxa is, xa must be in y axis or x axis, Yeah, because with respect to this you are integrating that. So, this is x a and yeah minus 1 by r a okay. So, what you get here is this kind of thing, okay. And yeah, actually when you plot x a versus 1 by minus r a you get like this, right. So, you take till whatever conversion you want x a and this area under the curve, I should have brought this one T by C A naught this side, okay. So, in fact I should not here also have to add here in this case 1 plus epsilon a x a, that entire thing I am plotting, okay. Yeah. So, this will give me directly T by C A naught, okay. Yeah. So, but if I plot this one constant density system, I have to plot this one as, yeah, this is variable volume, right, this is variable volume. For constant thing you have 1 by minus r a versus x a, again giving me like this, this is T by C A naught. So, that is how, because he uses these are even though I think earlier people have used these plots are called Levensfield plots minus r a, but I think originally also people used it, but somehow I think people call this one as Levensfield plots. And idea here is because he is an excellent engineer, okay. I told you. So, the reason is that this equation how complicated it would be we do not know, okay. So, if it is a simple one we have a mathematical expression, analytical expression, but in industry when you go for complicated reactions I do not have to really integrate that using mathematics, sometimes it is not possible to integrate. So, you have to go either numerical integration or you have to go for graphical integration. Graphical integration is this. So, you will simply calculate this x versus all this different x, because epsilon a you will calculate, you will know that, and then x and minus r a, because minus r a is nothing but some equation in terms of k C a, for example first order if you take. So, that C a again will have C a naught into 1 minus x a, but he is variable volume, that also will have this 1 minus epsilon a x a cancels and all that, but anyway. So, that you will have this function as only x and only x, that is nothing else, other things are constant, okay. So, then you can plot and then get the value, okay. That is not difficult at all, but these are the basic reactors which you also use in your wastewater treatment, okay. And of course, chemistry people also have to learn this because the catalysts. So, that is why these are the basic equations, even biochemical you use only these equations. This minus R A will be for them either Monod's equation or Michaelis-Menten equation, okay. So, even the other two reactors also same thing, okay, good. So, that is why these graphical procedures must be very easy for us, and I love graphs really, because I will tell you later, optimization only using graphs, again Levensfield method, wonderful techniques he has developed, simply drawing graphs, no mathematics required for optimization, okay. Using graphs, how do you optimize, that means minimum volume for maximum conversion or maximum conversion for minimum volume or given volume, okay. That also we will discuss later. There are many exciting things to learn, even though you have learnt once, because it will be more exciting now learning the same thing, okay, good. Anyway, I am thankful for you because you have forgotten everything. So, that is why I think all these things you may appreciate, okay, good. So, I think here we will stop. This is what is the batch reactor, but surprisingly you notice that in batch reactor there is no volume present anywhere. These are the final expressions, this is 9, this is 10. This is one final expression and this is another final expression, okay, C A naught, right. Where is the volume coming there? and the next class we will see where the volume comes, because finally you have to tell so much volume of the batch reactor, but any quantity you take you will only get time.